Hello, this is the section 6.3a lesson. This section is really a combination of topics from section 6.2 and 6.3, and we're going to be using some of the same examples from section 6.2 and 6.3 in this lesson. For this lesson, you're going to need your z-score table. Let's start off with an example that we saw in last section. Statistics class always lasts between 50 and 52 minutes. And so let's let our random variable x denote the length of a randomly selected class. And in that section, we showed that x has a uniform distribution. And so, for instance, in last section, we found the probability that x is greater than 51.5 minutes. So that means we found the probability that a randomly selected class is going to last greater than 51.5 minutes long. And to do that, we had our density curve here on the right. Here, the uniform distribution, the density curve was nice and flat on top. The height there was 0.5, and the class length was between 50 and 52 minutes. And so to find this probability, we went over to the number that we saw in the parentheses, drew a vertical line, and then we shaded to the left or the right. In this case, we shaded to the right because we're interested in x greater than 51.5, and the area of that shaded region is our probability. So to find that area, we simply found the area of that rectangle, which is the height times the width. The height is 0.5, the width is also 0.5, and so that's 0.25. Okay, so this probability is 0.25. Now what does that mean in a practical sense? Well, it means that about 25% of classes will last more than 51.5 minutes. So the point that we want to make here is that a percentage is the same as a probability is the same as the area underneath a curve. Now in this example, we were given an x value, 51.5, and we found the corresponding probability or a percentage. In this section, we're going to be doing the opposite. We're going to be given a percentage, and we want to find the corresponding x value or z-score. And those are what we call percentiles. And so to illustrate this, 50% of all classes last less than what amount of time? So here we're not given a class length, we're given a percentage or a probability. We want to find the corresponding class length. Okay. And so in terms of our density curve, what we're going to do here is we have an area of 0.5, which is 50%. This is an area to the left of some x value because we're dealing with something less than some amount of time. We're given the area. We want to find the corresponding value of x. Well, this is pretty easy to figure out. The total area underneath that curve is 1. We're dealing with half of that area. So that means this x value has got to be halfway between 50 and 52. So x has got to be 51. Okay? So 51, that's the answer to our problem. That number, that class length of 51, is called the 50th percentile of the class times. What that means in practical terms is that 50% of all of our classes are going to last less than 51 minutes. Okay? So we call this number 51 the 50th percentile. Now we've seen this word percentile come up before when we talked about percentiles of a set of data. And the 50th percentile of a set of data was a data value that was greater than 50% of the other values and less than 50% of the other data values. That's kind of the same idea here. This class length of 51 is greater than half of the other class lengths, and it's less than half of the other class lengths. So very similar ideas, just that these percentiles are calculated in terms of random variables rather than data. Okay. Now that one was pretty easy to figure out without doing any calculations. Here in the next example, we're going to do one that's going to take a little bit of arithmetic, but the idea here is the same. Let's find the 35th percentile of the class times. So this 35th percentile, the 35, is a percentage, 35%, or it's an area underneath the density curve. So here the area is 0.35. We shade to the left because percentiles are always shaded to the left. And that area is 0.35. We want to find the corresponding x value. Well, this one's not quite so easy to figure out just by reasoning through it. So we'll have to do a little bit of arithmetic. Well, the area of that rectangle is just the height times the width. Well, the area is 0.35. The height is 0.5. Let's find the width of that. Well, we can find the width doing some simple algebra. Just divide both sides of that equation by 0.5. do that arithmetic, and we get a width of 0.7. Now that's not the x value, that is the width of that rectangle. To find the corresponding value of x, we need to take the left endpoint there of 50 and add the width of 0.7 to get 50.7. So 50.7 is the 35th percentile of the class times. Practical sense, that means that 35% of the classes last less than 50.7 minutes. Now a couple important notes here is that 50.7 is a class time. It's not a probability, nor is it a percentage. However, the number 35 is a percentage or a probability. It's not a class time. So we've got two numbers here. One of them is a probability, the other is a percentage, or excuse me, one is a probability, the other is a class time. We need to make sure we keep the two straight, figure out which is which. Okay. So that's how we can calculate percentiles for a uniform distribution. Now we're going to talk about calculating percentiles for a standard normal distribution, and then we'll do a non-standard normal distribution. Calculations here are going to be a little bit different, but they're not terribly complicated. So to refresh our memory on doing this, let's look at this example of dealing with thermometers from last section. Remember what we have here is that these thermometers were tested by taking a reading at the freezing point of water. Now ideally that would be exactly 0 degrees Celsius, but the thermometers aren't perfect. Some read a little bit high, some read a little bit low. And so what we assume there is that the reading has a normal distribution with mean 0 and standard deviation 1. In other words, we assume that it had a standard normal distribution. And so last section we found, we did problems like this. If one thermometer is randomly selected, find the probability that at the freezing point of water, the reading is less than 1.58 degrees. So if we let z denote the reading of the thermometer, we want to find the probability that z is less than 1.58. And the way we did that was we sketched our standard normal bell curve with 0 right in the middle. We went over to 1.58, drew a vertical line, then we shaded to the left or the right of that line. In this case it was to the left. And then we found the corresponding area. Well, that wasn't quite as easy as with a uniform distribution. And so we found that by using our z-score table. So we went to the positive z-score table, went to 1.58, so down to 1.5 and over to column 0.08, and we get a number of 0.9429. That's the area or the probability. Okay. So our probability is 0.9429. What does this mean? Well, about 94% of the thermometers read less than 1.58 degrees at the freezing point of water. So the point of this this refresher example is again to illustrate that probabilities mean the same as percentages, which means the same as areas underneath the density curve. Okay. So now let's look at how we can calculate a percentile of from this standard normal distribution. So 67% of thermometers read below what temperature? So it's the same basic same type of question as what we asked with the uniform distribution, only now we're using a standard normal distribution. Okay? So in terms of our density curve here, it's the same standard normal density curve. 67%, that is an area or probability, and it's an area to the left of some z-score, and we want to figure out what is that z-score. Now, before we start doing the calculations, there's one important thing to note here, is that we know right away that this z-score is going to be positive. Now, why do we know that? Well, remember that the total area underneath our bell curve is exactly 1, and the curve is symmetric with respect to 0. So that means the area to the left of 0 is 1/2, the area to the right of 0 is 1/2. So because our area to the left is greater than 1/2, that means the z-score is going to be positive. If our area were less than 1/2, then our corresponding z-score would be negative. That's going to be very important in all the exercises we do. So continuing with example 3, the question was 67% of thermometers read below what temperature? In terms of our bell curve, we have an area to the left of z equals 0.67. And we want to find that z value. That z value is going to be our temperature reading. Okay? And so to find this, what we're going to have to do is go to our positive z-score table and look through the center of the table for an area as close to 0.67 as possible. Now we're not always going to be able to find an area exactly equal to the one that's given, but we're going to look for the one that's closest. And so if we look through the table, notice the upper left-hand corner we start at an area of 0.5. As we move down and to the right, the areas get larger. Well, near the top center of the table, we see an area of 0.6700. That's right at 0.67. So that's the corresponding z-score. And if we look at that z-score, it's 0.44. And so that's our z-score, 0.44. That's a z-score for which the area to the left is 0.67. That number, 0.44, is called the 67th percentile of the readings, and is denoted with this notation p sub 67. The subscript there denotes the percentile value, so 0.44. Now what does that mean in practical terms? Well, that means that about 67% of thermometers read 0.44 or less at the freezing point of water. So note here that the subscript 67 is a percentage or a probability or an area. The 0.44 is a z-score or a temperature reading. Okay. Now let's do another example dealing with the same standard normal distribution. Let's find p sub 12, the 12th percentile. Okay. So now in this case what we want is a z-score for which the area to the left is 0.12. Now it's 0.12 because that's our subscript 12. We also know that this z-score is going to be negative because that area is less than 1/2. Okay? So we're going to look through our negative z-score table for an area as close to 0.12 as possible. And if we just take a little bit of time looking at it, notice down in the lower left-hand corner, lower right-hand corner, we have two areas of 0.1210 and 0.1190. Both of those are pretty close to 0.1200, but they're both exactly 0.0010 away from our desired area of 0.12. And so what we're going to do is take kind of the z-score in between those. Notice that the z-score corresponding to 0.1210 is negative 1.17. And the z-score corresponding to 0.1190 is negative 1.18. So we're going to take the average of those two to be negative 1.175. So just add them up, divide by 0. So that's going to be our 12th percentile. Okay. So that's our 12th percentile. What does this mean? Well, about 12% of the thermometers will read negative 1.175 degrees or less at the freezing point of water. Again, note that subscript is a percentage and the right-hand side is a temperature reading. Now our last two examples are going to deal with this scenario of IQ scores, which we saw in last section. Adults have IQ scores that are normally distributed with a mean of 100 and a standard deviation of 15. Okay? Now notice that that is not a standard normal distribution. Remember, standard normal means that we have mean 0, standard deviation 1. We don't have either of those cases here, so this is a non-standard normal distribution. We want to find the probability that a randomly selected adult has an IQ that's less than 130. Now this is an example we did in the last section. We're doing this just to refresh our memory of what's going on here. And again, this is a non-standard normal distribution. Okay? So let's let x equal the IQ score. That's our random variable. Remember, when dealing with standard normal distributions, we always use z. When dealing with non-standard normal distributions, we always used x. We're going to find the probability that x was less than 130. And so to do this, we had a couple steps. First, we converted our x value over to a z-score using this formula. Z is x minus mu divided by sigma. Mu was the mean given in the problem. Sigma is the standard deviation given in the problem. And so in this case, we have a mean of 100, standard deviation of 15. We plug it in, do the arithmetic. We have a z-score of 2. So that means the probability that we want is equal to the probability that z is less than 2. So when dealing with z, that means we're dealing with the standard normal distribution. We know how to find this probability on the right. We sketch our standard normal bell curve, go to z equals 2, shade to the left. And then we go to our positive z-score table, look up 2.00, and we find the area to the left is 0.9772. Okay? So that probability is 0.9772. What does that mean? Well, about 97% of people have an IQ less than 130. Again, I want to stress the point that a probability is the same as a percentage, is the same as an area underneath the density curve. Okay. Now, let's find a percentile dealing with this non-standard normal distribution. Let's find the 10th percentile, p sub 10. So this 10th percentile is going to be an IQ score. It's an IQ score that's greater than 10% of other IQ scores or less than 90% of others. And or stated another way, it's an IQ score that separates the bottom 10% from the top 90%. Okay. So we're going to do this in two steps, kind of like when we calculated probabilities. We had two steps. We got similar steps, except they're kind of backwards because we're doing kind of the opposite of what we did in last section. So step one is to find the corresponding z-score. Okay. So we're dealing with the 10th percentile, so that means the z-score is going to have an area to the left of 0.10. Again, we know that that's a negative z-score because that area is less than 1/2. And so we go to our negative z-score, look for an area through the center as close to 0.10 as possible. And if we look there towards the bottom right-hand corner, we see an area of 0.1003. No other area is as close to 0.1000 as that, so we're going to take the corresponding z-score to be the one that we want, negative 1.28. So there's our z-score. Now we're not done yet because we're not interested in a z-score, we're interested in an x value, which is the IQ score. So step 2 is to convert that z-score into an x value, which is the IQ score. And we're going to do that with a formula that's equivalent to the formula for z-score, only here we've solved that formula for x. So x is mu plus z times sigma. Okay. And we use the same mean and standard deviation that were given in the problem. Mu is 100, sigma is 15. So we plug things in, do that arithmetic in our calculator, we get an x value of 80.8. So the 10th percentile is 80.8. What does this mean? Approximately 10% of people have an IQ that's less than 80.8. One last example. Let's find the 90th percentile. Okay. And so let's do our same two steps. Find the corresponding z-score. In this case, the area to the left of that z-score is 0.9. That z-score is going to be greater than 0 because the area is greater than 1/2. And so we'll look through our positive z-score table for an area as close to 0.90 as possible. And again, we may not be able to find one exactly equal to 0.9. If we look towards the middle of the right-hand side there, we see an area of 0.8997, and that's as close to 0.9 as we can get. And so we see the corresponding z-score is 1.28. So there's our z-score. Step 2, convert the z-score to an x value. We use the same formula, same mean and standard deviation as in the last example. And we do that arithmetic, we get 119.2. So that's our 90th percentile. What does this mean? Approximately 90% of people have an IQ that's less than 119.2.